All right. I'm doing this recording because I realized that this set is rather long, and given how little we covered last Friday, there will probably be a lot of questions that we can't quite cover today. So what I'm doing is I'm just gonna work through this entire set on this recorded video, and my plan is simply not to edit it because it's the editing part that really takes a lot of time. So I'll just to do this in one shot. That there will be some mistakes, things that I would have liked to edit it out, but it'll be a long, maybe 2 hour ish recording that um, will be much quicker to produce. Right, so I'm actually gonna reset and just do the whole set from start to finish. Because so here's the start. So this question, I've done this last time, but I think it's worth doing again because, uh, because. So this is going to be a common feature of many of the questions in this set, which is that they involve mechanical, tedious calculations that are um, um, that once you set it up, then it's kind of a matter of just working it through. Let me just change one thing real quick here. I'm seeing my microphone peaking, so I'm gonna just reduce this a bit. Okay, here, let's see. All right, so we'll just get started. So it asks for find the normalization constant. All right. So the question itself actually tells you what to set up. That's the hint. So you set that up. The the expression that you have to evaluate um, is from negative infinity to infinity of this expression psi absolute value squared. What it is a psi complex conjugate times psi dx. And I'm going to apply a little bit of simplification because for negative values of x, psi is 0. So this integral really simplifies to so my function is piecewise defined. I can imagine splitting my integral from negative infinity to 0 and then 0 to infinity. And the integral from negative infinity to 0 is gonna vanish. It's gonna be 0. So the only part that I actually have to evaluate is from 0 to infinity. And as I plug in the value or the expression of psi, what you will see is that this portion is real. So complex conjugate won't do anything. And this portion is complex, but see how this works out. So the function itself looks like e to the I minus I times, I'm just gonna collectively call the rest phi as a function of e and t. And when I multiply that with its complex conjugate, e to the plus I phi, they are going to cancel out. So, so this complex conjugate times the function itself, that's going to end up being the real part squared, a squared, x squared, e to the minus alpha x squared is going to become 2 alpha x, and the complex phase factor is just going to cancel out, so I won't bother writing it down. So times dx. So that's the integral I have to evaluate. And once I evaluate the integral, what that's gonna equal to is I set it equal to 1. And by setting equal to 1, I find what my a is. Um, For the evaluation of integral, I won't do it by hand. I think it might be doable by hand. You use, I mean, it is doable by hand. You use integration by part, I think. I guess you could also do integrating by differentiating under the integral sign, but I'll save that for another question. Here, I'm just gonna use one of the computer algebra system, one that to kind of free, available even offline is a Sage Math. I'm using the online version, but you can also do this offline. So let me type in the code for evaluating this integral. I need to declare my variables. And when I was testing it out, it turns out I have to enter some parameters. So say that alpha is greater than 0. And let's see here. Let me just close that. Um, and integrate from x squared times exponential of minus alpha times x, or minus 2 alpha times x, from x, with respect to x, from x equals 0 to infinity. And I think that's right. Let me click on evaluate, and let's see what we get. Oh, one time error. What did I do wrong? Is alpha. Oh, it's not assuming. It should have been assume. All right. Okay, so that's the result. So the integral here, when you finish evaluating. So when I did this computer algebra system stuff, I factored out a squared. So it's gonna be a squared times 1 over 4 alpha to the third power is equal to 1. So when you solve for a normalization constant, it'll be square root of 4 alpha to the third power. So that's for a. I won't do the plugging in the numbers. You can do that on your own. And one thing that I do see gives me confidence in the solution is, so for this evaluation of the exponential to work out, my a should have unit of inverse meter, so that a times x turns out to be unitless. So a has unit of inverse meter, which means alpha has a unit of inverse meter. So alpha to the third power should have unit of meter to the minus third, and take the square root. So that matches the unit here, meter to the minus 3 half. So everything is probably correct. All right, let's look at part B. Find the probability that the particle can be found on the interval 0 to 0 to L. So this pairs up with what we did in part A, because what we did in part A is what we got by imposing that. So this quantity here, the absolute value squared, this is my probability density. It's showing the probability that particle is within from coordinate x to x plus dx. That's what this is. And in order to make that probabilistic interpretation work, we impose this condition so that when you integrate over all space, it becomes 1. That's what we've done. So having found, so that's what we've done when we we normalize this probability density in part A. So having normalized in part B, what we can now find is, all right, we know the normalization constant. So over all space, we have 100% chance of finding the particle somewhere. Now the question is, what is the um, what is the probability? It's within certain interval. So to calculate that, you just calculate the area under the curve, or the curve being absolute value of psi squared, or psi squared, that is absolute value squared, over the interval. Here, the question gives the interval of 0 to L dx. So that's it. You plug in the expression for A that you found in found in part A. Then let's see here. Let me do some of the simplification in my head. So I get this coefficient 4 alpha to the third power. And this is going to be an integral from 0 to L being 1 over alpha. 1 over alpha. Let me scroll up a little bit. X squared e to the minus 2 alpha x dx. I do the same simplification that um, I did the last time. So, um, all right. I think I'm gonna do this integral using. Wait, sorry. Why am I writing equals 1? So it's not equal to 1. And the question is asking me to find that. So let me do this integral the same way as before. So I think I can just take this and modify it a little bit. So instead of going from x equals 0 to infinity, to going from x equals 0 to 1 over alpha. Everything also stays the same. And oh, I think I want to simplify that. So let me put it through full simplify. I think that's the right function name. Maybe it's without underscore. I don't use SageMath all that often. All right. I think maybe what I need to do is let me put this into solution. And I think I can do solution for simplify. Okay. All right, that looks rather complicated. I wonder if it'll simplify better if yeah, I think it's gonna simplify better if I multiply by 4 alpha to the third power, because I'm saying this. Yeah, so let me do it this way. I'm gonna do solution times 4 times alpha to the third power. And I think it's gonna be a numerical thing. Let me double check. Uh, Let me do a full simplify again. Yeah, that's totally numerical. So let me just put this through n. I think n is the function that gives me the numerical approximation of the result. So yeah, 0.323. That's the numerical answer. 0.323. Oh, let me submit it and make sure I'm on the right track. Yeah. um, and yeah, that's it. So as I was saying at the beginning, these questions are rather simple. What's potentially complicated is that it's asking for integral of non-trivial expressions. But if we use computer algebra system, then that's pretty easy. Really, the part that takes the most effort is the setting up the necessary expressions. By the way, I'm seeing my sound to keep peaking, so let me just reduce my microphone volume again. I guess I shouldn't have raised this so much at the beginning. All right, so let's keep going with part C. So it asks for find the expectation value of position. So in lecture we covered expectation value quite a bit. So I'm just gonna rely on that and just write down this expression for expectation value and just work my way through. So the expression for expectation value, it's over the whole all space. So it's technically from negative infinity to infinity, but I'll simplify it. Um, the psi complex conjugate times the operator, in which case, in this case, this is just the multiplication by x times the wave function itself, the and integrate it with respect to dx. That's my coordinate variable x. Do mind the two different ways in which x means in this particular representation. And I'm going to do the same simplifications again because when I go look at my definition of psi, for the negative values of x, my psi is 0, so my integral will simplify down to just 0 to infinity again. And note how this multiplication by x, it doesn't really change anything. Um, it has no impact on um, the wave function. So all the simplifications I did before regarding the complex conjugate times the function itself for the phase factor, they're gonna cancel out again. So when I finish writing this down, um, it'll really look like x multiplied to what I had before. So integral of from 0 to L a squared, I'll write that down as a squared for now. And what I had before was x squared times e to the minus 2 alpha x dx. And really the only change here is that instead of x squared, now I have x to the third power because there's this additional factor of x multiply to the expression that I'm integrating. So, oh, and oh, sorry, it's not from 0 to L, it's from 0 to infinity. So I'm integrating over all space again because the probability that, yeah, so I'm not arbitrarily limiting the interval that I'm looking for the particle for. For calculation of the expectation value, you do have to do it over all space, over all possibilities. So with that, I guess I'm gonna bring up my computer algebra system again and just modify this expression as I need to. So the integral that I'm doing is gonna go from x to the third power times e to the minus 2 alpha x, and x now goes from 0 to infinity again. And for the final calculation, okay, I don't know if it's gonna be numerical, but so I will multiply the resulting solution with 4 times alpha to the third power. That's multiplying by a squared, and I'll hope it'll simplify. So I'll put it through full simplify again. Okay, so let's see what we get. Oh, that's rather simple in terms of alpha. So this entire thing, when you evaluate it, is gonna be 3 divided by 2 alpha. Um, and the units work out because alpha has unit of inverse meter. And when you calculate the expectation value of position, you do expect the answer to be in the unit of meter or reciprocal of inverse meter. So yeah, plug in what alpha is. Well, that should give you the answer, up to the power of 10. And I'll leave the number plugging in to you. Okay, let's keep going. Oh, part D, that is expectation value of kinetic energy, and it's the same deal again. You just have to um, chalk it through the expressions. So it's the same basic expression that you are going to be using. I guess, yeah, so let me just write it down first and we'll pre-simplify it a little bit. So it's psi, yeah, the complex conjugate of the wave function times, for the operator for the kinetic energy, it's gonna be momentum squared over 2m times psi. And you integrate it over all space, the same as before. Um, Now, one thing I do have to be careful is that let me write this all out. I think here it'll actually be useful to do this, so I'll try to do that. So since I'm writing it all out, I guess I will do one simplification, which is the integral is going to be from 0 to infinity, since for value of x negative, the integral will still vanish to 0. So my um, complex conjugate of wave function is gonna be a times x times e to the minus alpha x, and the complex phase factor is where I have to be careful. E to the plus I e t over h bar times. Let me write out the form of the operator. So the the operator for the momentum is minus I h bar. The so this is the operator for momentum squared. It should be minus I squared, which will give me minus 1, h bar squared, which will give me h bar squared, and this differentiation operator applying twice, that will give me derivative with the second derivative with respect to x. So that's gonna be my momentum squared operator multiplied by 1 over 2m. So it's gonna be minus h bar squared over 2m, and the second position derivative of the wave function again. So or I guess wave function for the first time before it was complex conjugate. So the wave function is a times x times e to the minus alpha x times um, e to the minus I e t over h bar, and do the integral with respect to x. Okay, it looks like some things actually do simplify, because the complex phase factor, it only relates to, it doesn't have anything that depend on x. So it's not gonna be changed by this derivative with respect to x. So they will just cancel out. So all I'm dealing with are, let me write down a bit of a pre-simplified version. Let me factor out all the constants. So I have a squared, and then times minus h bar squared over 2n, and I think the rest are not constant. From 0 to infinity, I have x times e to the minus alpha x. And note how this time I'm not just freely moving this function around, because I have this differentiation operator, so I have to be careful about the order. So I have this second order derivative with respect to x of x times e to the minus alpha x. All right. I think I'm gonna, from this point on, use my computer algebra system. Let's see here. So let me just do this step by step so that I know what I'm doing here. And just I'm commenting these out so that for a few of my test calculations it doesn't mess up. So I think the function for differentiating is called the differentiate. So So I want to differentiate x times exponential of minus alpha times x with respect to x. I think that's the right syntax. Let's see. Oh, I don't know. Is is it just a D? Let me give that a try. No. Um. Mm, I don't diff. Okay, it's a diff. All right, that looks about right. So I need to do it twice. I'm pretty sure differentiation function actually has an optional parameter which will help me do a second order derivative in one go. Oh, I guess derivative was the actual function name. Um, it's yeah, derivative fu 3. I think that's the way to specify the order of derivative. Okay, so let me do it this way. Um, so derivative of this second order. All right, that's the second order derivative. And what I need to do is do this. So I have x times exponential of minus alpha times x. That's my first part of the function. And I have the second order derivative of that same function, which is here. And I'm going to integrate it with respect to x from 0 to infinity, all the while assuming that my alpha is greater than 0. Um, and I think I'm gonna take the resulting solution and do multiply it by 4 times alpha to the third power. That's my a squared. And let me actually multiply it by minus 1 as well. And so I'm hoping that'll give me some kind of a positive expression, and I'll multiply that by h bar squared over 2m. That'll be my final answer. So evaluate. Oh, alpha squared. All right, that was remarkably simple. Uh, that's, I guess, yeah, sometimes quantum mechanical calculations just work out that way. After you do a lot of tedious work, so it's h bar squared over 2m times alpha squared. After you do a lot of tedious work, it ends up being relatively simple result. I think that kind of simple result is what tells you you must have done something right. Um, for this, let me plug in the numbers just to make sure that I did it right. Oh wait, it says leave your answer in terms of h, m, alpha, and other. Oh, I guess I'll do that. So it's gonna be alpha. Let me make sure alpha is one of the variables. Okay, alpha squared times, and I have to be careful with the h bar because the system doesn't recognize h bar, so I had to write it down as h over 2 pi. That's the only way it'll recognize it. Squared divided by 2m. Okay, that should be it. All right, so that's the result. Okay, that was the first question. Yeah, that took a while, so this might actually take longer than 2 hours. But I'll just work through the whole set, and in the resulting video, I'll just timestamp it later so that people can easily skip to the question that you had a question on. All right, question number 2. And I'm keeping this, yeah, I'm doing this split screen thing so that it's easier for me to uh, keep track of my work and write down things I need to. All right, it says time-independent wave function of a particle with mass m is given by that. Oh, so I guess it's defined. Oh, I see. The way the alpha is positioned, I think it's defined so that you get something that looks kind of like a standing wave over a limited region of space, and zero outside of the limited region. So okay, I think mechanically it should be remarkably similar to what we just did. So let's remarkably similar to what we just did for question number one. So we'll just go through it without a lot of explanation this time. So I'm setting up the normalization condition, psi absolute value squared dx. Now, I note that the wave function in this time independent wave function is entirely real. So I can simplify this quite a bit. I can, for one, set my limit of integration from negative pi over 2 alpha to pi over 2 alpha, and um, just to write down the function as a squared cosine squared alpha x dx. Now I'm gonna do a substitution that will make use of computer algebra system a little bit simpler. In fact, simple enough that you can maybe even do this on a graphing calculator. So I'm gonna make this substitution. U is equal to alpha x. That simplifies something quite a bit, which let me show you. So with this substitution, you have du is equal to alpha dx, or the this substitution tells you that dx is equal to du over alpha. Now, this is how I like to do U substitution or algebraic substitution with the definite integrals. As I'm substituting in the new expression, I also do the limits of integration. So, so let me write this out as x is equal to u over alpha. So as I write out the integral, I do the substitution of the limits of integration. So I plug in minus pi over 2 alpha into oh wait, I didn't need to do that. So to get the limit in terms of u, what I do is I plug in minus pi over 2 alpha into the x here. Then resulting value gets me the lower limit in terms of u. So that's going to be minus pi over 2 alpha times alpha. Alpha cancels out. So I'll get minus pi over 2. And for the upper limit, it'll become pi over 2. And I have a squared, that doesn't change, times cosine squared of, instead of alpha x, I have a u, times, instead of dx, I have du over alpha. And what this substitution has done for me is it separated out expression into these two parts. I have a squared over alpha, that's one algebraic part, and note the special feature of this remaining part, minus pi over 2 to pi over 2 cosine squared u du. This is an entirely numerical expression. So this is what I mean. You could do this even in a graphing calculator if you wanted to. I'm going to, I have a feeling that's going to end up in something very simple, but let me just do a little bit of overkill and do this integral anyway. So I'm integrating from integrating cosine of x squared from in terms of x. X here, quote unquote x here, is a dummy variable, so it doesn't matter what I call it, whether x or u. So it goes from minus pi over 2 to plus pi over 2. My apologies for the noise. I am putting noise filter on the audio, but I think some of that outside the car noise is probably coming through. Um, Evaluate, and yeah, I figured it's gonna give me something super simple, 1 over 2 pi. Yeah, so if you had done this calculation in your graphing calculator, you would have gotten, um, oh, I'm pretty sure that means 1 over 2 times pi. So, uh, all right, 1 over, let me write out 1 over 2 times pi is in the numerator. All right, so this is the expression you have for normalization condition, that a squared over alpha times 1 half times pi is equal to 1. So solving this for a, you get a is equal to, let's see here, square root of 2 alpha over pi. And looking back at here, um, oh, I don't know if this tells you anything. Alpha does have unit of inverse meter. Um, and I will tell you that A having unit of, oh yeah, actually I guess the question gives it away. A should have unit of minus one, um, minus 1 half. So, uh, so yeah, that I think all works out. So plug in the numbers yourself. I'm just gonna leave that there. And it asks now for the probability that the particle can be found on the interval from, yeah, this is a small portion of the interval. It's not quite 1 half. Yeah, this here, so this was part A. So for part B, the calculation kind of goes the same way it did for problem 1. So for B, it's the exact same calculation you did in part A, except instead of your integral going over all space, it's explicitly going from 0 to 1 half alpha, and the integrand is the same, a squared, yeah, a squared cosine squared over alpha x dx. Um, And I should imagine doing the same u substitution as before, because this will again help me simplify the expression so that the resulting integral is doable, even on a less sophisticated computer algebra system. So with that substitution, my limit of integration becomes, from 0 to, 0 times alpha is 0. 1 over 2 alpha times alpha is 1 half, and the remainder of coefficients I have a squared, so that's gonna be 2 alpha over pi square root squared, times cosine squared of alpha x, that's u, dx, that's du over alpha, so let me pull out the alpha, times du. Oh, alphas cancel out, how convenient. So, okay, so I think when I do this calculation, I'm gonna get something that's totally numerical. So let me work through that. It's gonna be, so same integrand, x this time going from 0 to not pi over 2, but just 1 over 2. And let me actually multiply this to 2 over pi in this here, and I'll just put this into numerical evaluator thingy so that I get the numerical answer that I'm expecting. So the area under the the curve of the probability density function is 0.293. Let me plug it in so that I have some indication that I'm on the right path. And yeah, there you go. Um, It asks find the particle's average position. Oh, yeah. You could have probably guessed the result correctly. And this is what I mean. The answer, when you go through the whole thing, it's gonna end up being zero. Because how would you? So I mean, I'm relying on my intuition here. Here's one way you can figure out the answer must be zero. So let me give you more detailed justification why answer there ought to be zero. It's because when you look at your wave function, it's a actually I guess you know what you don't well let me write down the wave function. 8 times cosine of alpha x. And what matters here is that this is defined over a symmetric interval. X goes from some negative something to positive same thing. So it's defined over symmetric interval. So when you do the integral, it's over this symmetric interval. And when you do this integral minus lambda to lambda, and for the operator x, it does end up being just x times psi absolute value squared dx. And this is the thing to notice. When you look at the functional form of cosine squared alpha x, this is an even function. The function has an even symmetry. And x is an odd function. So odd function times even function gets you odd function. So you are integrating over a symmetric interval over an odd function. That is why this should be equal to zero. So, and there's also, if you have enough physical intuition, the physical intuition will tell you that it should be zero there. So that's it as far as it goes. And it asks for the particle's average momentum. And here, again, it says you could have probably guessed the result correctly. And the result is that it's zero. I guess I might have been giving away too much by telling you that you could guess it. But let me go through the argument again. So here, it takes a little more step than in C to give the correct justification, the mathematical justification. You actually do need the expression for psi, because in the case of the momentum operator, you do have to start out with the operator sandwiched between the wave function. So psi complex conjugate times minus I h bar over, oh wait, I guess just minus I h bar. Um, minus I h bar, the derivative with respect to x, and it's this derivative that complicates things somewhat so that you can't just freely rearrange the terms here. Now, when you imagine applying this derivative operator, then so you know it applies to this portion, cosine of alpha x. So out of this part, you get something that is proportional to sine of alpha x. I mean, there's a minus sign, but that doesn't matter. So what you have again is the function on this part, you know, cosine of alpha x. Cosine of alpha x, so this is proportional to cosine of alpha x. This is even. Sine of alpha x, that's odd, over a symmetric interval. So even function times odd function over a symmetric, integrated over a symmetric interval, they're gonna integrate to zero. That's why it's zero here. Now, part E is where you do have to be careful. The easy mistake to make is I think, oh, my momentum was zero, so momentum squared over 2m, that's gonna be zero again, and that's not the case. If you paid attention for the infinite square wall problem, you know that that's not the case. So with the party, you can kind of see in the hint that it doesn't hint that you can guess the result correctly. That's because you can't. You actually have to go through the calculation. So you have to set up the calculation. That's quite similar to what we did in problem one. So my so the thing that I'm setting up is integral over all space of the complex conjugate of the wave function times the kinetic energy operator, plugging in the expression for the momentum operator. It's gonna end up being, let me write it out, minus, minus comes from minus I squared, h bar squared over 2m times the second position derivative. And that operator is acting on the wave function dx is equal to 0. All right, I think I might actually be able to do this by hand if I do this carefully. So let me write it out. My integral over all space becomes integral from over the parts where my wave function is not 0. So that's gonna be from x equals, well, I don't remember, uh, minus pi over 2 alpha, uh, minus pi over 2 alpha to pi over 2 alpha, and my because my wave function is real, the complex conjugate is just a times cosine of alpha x times minus h bar squared over 2m. And I think I can actually do the second derivative of this in my head because it's simple enough. So I apply chain rule to cosine of alpha x, and each application of chain rule brings out a factor of alpha. So the first derivative will be minus sine alpha x times alpha. The second derivative will turn sine back into cosine. So when I take the two derivatives of psi with respect to x, what I will end up with is the coefficients a times alpha squared times, now the derivative that I did, minus sine, sorry, not sine, sine that turned it back into cosine, minus cosine alpha x dx. Note remarkable simplifications here. The minus signs cancel out, and let me factor out a bunch of things. So when I do, so I'm gonna factor out h bar squared over 2n, and oh, let me factor out alpha squared, and I think the rest I'm just gonna leave not factored out because it's one place where I can identify the functional form and identify that something we've done before. So the remaining terms are a squared times cosine squared alpha x dx. Does this look familiar? It should. It's what we did way up in part A. That was the expression that we normalized, which means we actually set this equal to be 1 by setting the proper coefficient for the normalization constant. So I don't actually have to do this integral. This was set to be equal to 1 by the circumstances. So my answer here for kinetic energy is h bar squared of alpha squared over 2m. Ah, that's looking familiar. Um, is that actually exactly the same answer as what we did in question 1? Yeah, yeah, I guess that's just totally accidental. But oh well, let me just do copy and paste of that. Now, don't always expect your kinetic energy to have that form. Here, it's just the way the wave functions were specified. It's a happy accident. Okay, so that's problem 1 and 2 are meant to, they were designed to be similar to each other, so that it gives you some practice. Let me move on to the next question. I have a feeling this is my yeah, follow the steps outlined in the problem. If you run into difficulties carrying out the derivatives, feel free to use mathematical world from alpha. And well, what it is it's a tutorial question. I'm just supposed to work through it, and so I'll do that. So this is question number 3, and yeah, that's the time-independent Schrodinger equation with the harmonic oscillator potential. That's right. And one thing I'm gonna tell you what I'll do is I'm always gonna write this as a h bar when I'm doing algebra by hand. I'll just plug in the h over 2 pi at the end when I'm plugging in the answers. And this question does what I told you that I would always do with things like harmonic oscillator potentials. I'm gonna tell you what the solutions look like. I won't ask you to solve it yourself. Um, so this these two wave functions give you equation for the two lowest energies. This is the ground state with the quantum number 0, n equals 0. And this is the first excited state with the quantum number n equals 1. And yeah. Okay, and really, and what this is getting you to add is the result that is derived in the textbook, or I don't know if it's actually derived. It's given in the textbook that the energy levels of simple harmonic oscillator. Let me make sure it looks like n is given by n plus 1/2 times h bar omega, where omega is the expression occurring in the potential form for the wave function, for the Schrodinger equation, or the natural oscillation frequency of the oscillator. So that's what's in the textbook. Now you can't just plug this in. It's broken this way so that you have to go through the calculations. So let's go through that. So I'm doing this for the ground state. And what the question is asking me to calculate is minus, so this is for A, minus h bar squared over 2m times, okay, I need to do the one second order derivative of the ground state, a naught times exponential of minus m omega x squared over 2h bar. Oh, I can see that it's gonna be a bit of a pain. The first order derivative is fine. You do chain rule, so exponential of, so you do take the derivative of the inside, multiply by that, you are done. Now the problem is the derivative of the inside includes a factor of x because it becomes 2x. So the second derivative is gonna make me use product rule and then chain rule. It looks like a lot of work. So what I'm gonna do is use computer algebra system. In the part that's gonna be a lot of a hassle, so that so this is a hybrid approach of doing a lot of things by hand, but not everything by hand. I think I can combine all these coefficients in front and just call it alpha. So I'll declare the variables x and alpha. And to do the derivative, so I'm going to imagine factoring out a naught. It's not a function of x, so I can do that. And for the derivative, I have to take the derivative of exponential of minus alpha times x squared with respect to x, second order. Yeah. And let me also full simplify. Because I think after you do all the tedious calculations, some of the things actually do simplify and factor out. I just don't want to do it myself. Yeah, this is what I mean. This part actually factors out to the right or to the left. So I can kind of rewrite this again. That's going to be part of my result. So let me just write down all the terms here. I have minus h bar squared over 2m times a naught. I factored that out. Oh, actually, you know what? Let me not factor that out here. I'm gonna recombine a naught with the exponential. that'll give me something useful to do. And I need to write out all these coefficients that came out, including x squared. So it's gonna be, ooh, let me just distribute the two. So it's gonna be 4 times alpha squared times x squared minus, I distributed the two, 2 times alpha. Yeah, and it doesn't simplify any more than that. Oh, and I have times a naught, and then this exponential term that factor dot, exponential of minus, well, I could write it as alpha. Let me just write it out as m omega over 2h bar x squared. This, I recognize it as the wave function psi naught. So that's actually written into part of the question. This is psi naught on factored out to the right. So I'll leave that be. So yeah, so I just need to write this in here. Yeah, there's really not much more I can do. Maybe I guess I can do one thing, which is I can uh, I could distribute this in, but let's see here. No, it's gonna be a whole lot of a hassle, so I will just write it out. Yeah, yeah. So minus h bar, h over 2 pi squared divided by 2m times, and the rest I'll just write it out. 4 times alpha. So instead of alpha, it ought to be yeah, yeah, m times omega divided by 2 times h over 2 pi. This could be simplified a bit. I just choose not to because the whole thing is depressingly complicated. Squared times x minus 2 times what amounts to alpha, m times omega divided by 2 times h bar, or h over 2 pi. The simplification takes place after part B, I think. So yeah, let me submit that. Make sure I have it right so far. Do I not have it right? Let's see, h bar squared over 2m, 4 times, oh, I forgot the x squared. X squared, all right. Now I should be correct. All right. Yeah. For psi naught, add the above kinetic energy term to the potential energy term. Simplify the resulting expression. Cancel out what cancels out to fill the blank below. Um, so the first term calculation we just did. So what we are adding to here in B, so we have this complicated thing, which is, let me call that, I don't know, B. So in B, what we are calculating is this whole complicated thing plus 1/2 omega squared x squared psi naught x. So I think it's gonna be useful to just distribute everything out and simplify. And let me just remember alpha is m omega over 2h bar. So let me just distribute everything out. When I do that, what you get is minus, so h bar squared over 2m times 4 alpha squared. That's gonna be m squared omega squared over 4 h bar squared times x squared. That's the first term, plus 2, and for the second term, minus 2 cancels out, so I have h bar squared alpha over m or let me write out what alpha is. Alpha is m omega over 2h bar. And oh, I almost forgot. Both of these have the psi naught multiplied into them. Psi naught, psi naught. And so this is what we had from part A. Let me add the part from part B, which is the potential energy term. Plus 1 half m omega squared x squared psi naught of x. Now watch this simplification. This first term here, 4's cancel out, 1 factor of m cancels out, h bar squared cancels out. So this entire expression here is minus 1 half m omega squared x squared, which is the exact opposite of plus 1 half m omega squared x squared. So this whole thing cancels out this whole thing. So the only term that remains is this one. It's quite remarkable how it simplifies. And this actually simplifies a little more because m's cancel out, 1 factor of h bar cancels out. So you have h bar omega over 2, which I hope reminds you of this formula that's in the textbook. N equals 0, you get h bar over 2. That is the result you would expect, and that is the result that you get when you go through the detailed calculation. So h bar times omega divided by 2. That's it. And do I want to do psi 1? Yeah, I don't think I want to do... I will just... let me do psi 1. I don't think it's going to take that many more minutes. So for part C, what you do is basically the same. So comparing psi 0 with psi 1, I notice that the only difference between the two is this additional factor of x, at least so far. I think a higher energy level ones are even more complicated, but first excited state, it's still relatively simple. So in terms of how I did it, I think it's fine because I can just modify this to say x times, and then full simplify. So when I do that, so yeah, I'm gonna have this more complicated expression of alpha and x, but I can deal with that. Actually, I would factor out 1 factor of alpha so that I can put together a psi 1 again. And when you have that, then yeah, so let me just plug this in. Let me so for part C, I'm gonna copy down this result, that double derivative of x times e to the minus alpha x squared gave me, let me see here, I'm gonna distribute the two, so it's gonna be 4 alpha squared x squared minus 6 alpha times, I factored out an x times e to the minus alpha x squared. All right, so with that differentiation result in hand, I can do the rest of the calculation relatively easily. So I have minus h bar squared over 2m times this thing, more or less. I mean, without the a there. But this whole thing is my psi 1. So this whole thing, when I do that, what it's going to end up being is minus. Yeah, and I think there's a way to write down h bar fewer times. Let me do that. So alpha, from memory, it's m omega over 2h bar. So I can actually write this as minus 1 over 2m. Actually, let me just distribute the whole thing. I think that's going to look a lot simpler. So distributing minus h bar squared over 2m, I get um, minus h bar squared over 2m. Let me plug in the alpha as I go. 4m squared omega squared over 4h bar squared minus 6. Wait, was there really? Oh, all right. I guess 6m omega over 2h bar. Um, and then the red. Wait. I said I would distribute and then didn't. Yeah, let me actually do it this way. So it's fine. I haven't distributed it yet, and this whole thing multiplies to psi 1, I think. So far, so good. And in the next line, I'm going to distribute. So for the first term, I have h bars canceling and force canceling, 1 factor of n canceling. Oh, yeah, I think I've seen this before. Minus 1/2 m omega squared times psi 1x. So that's minus plus I have 3m omega over h bar. 1 factor of h bar cancels, 1 factor of m cancels. So I have plus 3 halves. Oh, h bar omega. Yeah, I think I might have anticipated that. Times psi 1 of x. All right, let me enter that in. So it should be minus m times omega squared, over 2 plus 3 halves times h bar h over 2 pi times omega. And just for my sanity, let me just do a parenthesis here. I mean, I don't think it matters either way, but I want to. Did I forget something? Oh, I forgot x squared. Yeah. There's the x squared there. I forgot to write it down here when I put it in. So there should have been x squared there. So, yeah. A lot of tedious algebra. All right, and this time actually having done this simplification actually makes my next step pretty easy because the potential energy term cancels that out. So I'm just left with the second term that I can just almost copy and paste into this input here. So yeah, this is kind of practice through the calculations step by step, they're not hard because especially here, all you are doing is derivatives. I could have even done this by hand. It's just that it gets tedious, and you see how forgetting a small term like this leads to incorrect answer. So this is where attention to detail really matters. So with that, let me just continue on. That was my question 3. All right. Let's look at question 4. Oh, you know what? This is pretty easy. It's transitioning from uh between adjacent states of harmonic oscillator. So the energy difference is gonna be h bar omega. So omega, it'll kind of come very simply from the formula. So I'm gonna not do it. Um, yeah. I mean, do I want to? Uh, I mean, I could. So I'll just do it in a calculator without a lot of complicated expression justifications. So I'm thinking of my expression for the speed of light. C is equal to f times lambda. I'm given lambda. So for f is c over lambda. So 3 times 10 to the power of 8 divided by lambda, or 436 times 10 to the power of minus 9. Now that's a frequency in hertz. they want frequency in radians per second. So I need to multiply this by 2 pi. So that's it. In scientific notation, 4.32 times 10. Okay, so 4.323. 323. Oh wait, why is that not correct? um, what is its frequency? Um, that should have been right. Oh. So let me times 10 to the power of 15. Yeah. All right. Let's keep going. Okay. Suppose that the vibration of a hydrogen molecule can be modeled as a simple harmonic oscillator. Oh, yeah. So yeah. So here it's actually this question can be done rather easily if you remember some things about quantum simple harmonic oscillators that you learned in physics 4a, which is this result here, which actually does come into the discussion of quantum harmonic oscillator as well. It's this result that natural frequency of oscillation is equal to square root of k over m. And in fact, here it's kind of done in reverse. They define this spring constant k by observing the natural frequency of oscillation and work it backward. So we are kind of doing it backward, but it's fine. So omega is the square root of k over m. So I think that gives the frequency f right away. You just plug in the numbers, that gives you the frequency. And where that's so what are the energy and wavelengths of the emitted photon when the molecule makes transition between third and second excited states. And what's important here is that these are adjacent excited states. So given the energy levels of the form n plus 1/2 h bar omega, the difference between adjacent energy levels is gonna be h bar omega, or I guess h times frequency, since h bar is h over 2 pi. So yeah, so here it should be just frequency times Planck's constant. If you use Planck's constant in electron volt units, you don't even have to convert. Photon wavelength, so just go from knowing the frequency and plug in use c is equal to frequency times wavelength. So wavelength is speed of light divided by frequency. So that should be pretty simple. Let me move on. Question 6. Oh yeah, this is a potentially long, tedious calculation. So I'll work through this here. So this question gives you some, it's written as a tutorial question, so it's giving you some guidance, help with a lot of its calculations. So let me work through that. It's giving you the, so this is question number 6. It's telling you the normalized ground state wave function. Psi of 0 x is, let me write it this way, m omega over pi. Again, I'll write down h bar for h over 2 pi. Here it's written as h over 2 pi because the grading system doesn't recognize h bar. Exponential of minus m omega over 2h bar x squared. Yeah, I hope you recognize this functional form. And what's different now is the question has given you the normalization constant as well. Okay, and and it says it exhibits the minimum possible uncertainty, and as we go through this tutorial exercise, we will show that it actually does work out that way. All right, mathematical preliminary. Oh, yeah, at some point I'll need to be able to do this integral, and I could always do it using computer algebra system, but I want you to illustrate a particular mathematical trick that allows you to do this sort of calculation quickly and easily by hand, and that's what part A is walking you through. You do have to start out with some foreknowledge that this particular integral, which is actually not easy to do, e to the minus alpha x squared dx, um, it's a widely known integral. This is what's called the Gaussian function, and I think in calculus 3 you learn of a technique using three-dimensional integral to work out what this is. So assuming you've covered this somehow and know that the formula for this is square root of pi over alpha, you can actually derive a related integral of this form. The related integral being integral over all space of x squared e to the minus alpha x squared dx. So this is how you do it. You imagine taking this expression and differentiating it with respect to alpha. Forget for the time being that alpha is a constant parameter. We are treating it like a variable. And when you do that, on the left-hand side, you can swap the order of the integral and derivative for well-behaved functions. This is something you can do. I think there's a theorem in calculus that um, uh, proves that for well-behaved functions. So, but we're gonna take that for granted. So when you swap the order of integral and derivative, what you have is derivative with respect to alpha of e to the minus alpha x squared. So treating this as my variable, the derivative there becomes minus x squared e to the minus alpha x squared. So this is I'm using chain rule. This is the derivative of the inside, derivative of the outside for exponential didn't change. So this portion is what the question is looking for, minus x squared. Okay, that's the left-hand side. For the right-hand side, you have to work out, so this is a square root of pi, that's constant, I can ignore that. So what I'm taking derivative of is the polynomial function of alpha to the power of minus 1/2. So the derivative of that is going to be minus 1/2, and then alpha to the power of this minus 1, so minus 3/2. So let me choose to write it so that it's all under square root. So it's going to be pi over alpha to the third power. So that's going to look this way. Minus 1/2 times square root of pi over alpha to the third power. Yeah, that's it. And you do have to go one more step to actually derive the formula that you will need. And I guess it works out to be just canceling out this minus sign common on both sides. And let me actually simplify this a little bit more into square root of pi over 4 alpha to the third power. I think that's going to be useful in a couple different places, because I'm kind of looking at this and doing. Anyways, so that was an A. Just as it's saying, mathematical preliminary, making sure you have the right integration formula that you will need later to do this by hand. Okay, so it says calculate the expectation value using the normalized wave function psi naught of x. So the formula here is simple enough. This is the procedure you learned of calculating expectation value. Oh, wait. Okay. I need to be able to see the wave function while I'm writing down. So the expectation value of some operator x squared is gonna be equal to integral over all space of the wave function complex conjugate, or in this case, this wave function is real. So it's just gonna be the wave function itself, fourth root of omega over pi h bar times exponential of minus m omega over 2h bar x squared. That's the wave function times the operator for x squared, that's simply multiplication by x squared, times the wave function again, that's gonna be, writing it as x looks super confusing, times, I need to write it on the second line, so it's gonna be the same thing again, square root of fourth root of omega over pi h bar times exponential of minus m omega over 2h bar x squared k dx. All right, that's my entire expression. And staring at it, so the multiplication by x squared doesn't depend on order, it commutes. So I can just combine these two wave function forms without too much problem. So let me do that simplification. So I have, this is what I have. These two coefficients multiply and they are constant. So I'm gonna pull it out of the integral. I have a square root of m omega over pi h bar. And then integral of from negative infinity to infinity x squared. And when I multiply together the two exponential terms, this factor of 2 in the denominator goes away. So it's going to be exponential of minus m omega over h bar x squared dx. And this is where I use the integration formula that we derived. This integral is going to end up equal to square root of pi over 4, and let me write down the reciprocal of alpha squared, alpha to the third power. So alpha is m omega over h bar, so the reciprocal is h bar over m omega to the third power. So m to the third and omega to the third. All right. So when you imagine this first coefficient multiplying to this second term that comes from the integral, you see quite a few cancellations. Pi's cancel, one factor of omega, h bar cancels out one factor here, one factor of omega cancels out one factor here, one factor of m cancels out one factor here. So, this is h bar over 2m omega squared. So this whole thing is just h bar over 2m omega. That's my x squared, which for this state, as explained above, it as explained. Wait, where did I explain it? Oh, as explained here, the expectation value of x squared is the expectation value of the standard deviation squared. So, all right, I'll just write out h bar, h over 2 pi, divided by 2 times m times omega. And let me leave it up to you to work, see that this is the correct unit, that this combination of factors does give you the length squared unit. Yeah, let me leave that for you. And let's work out C. So for part C, I have my part B on screen so that I can copy over the parts that are as needed. So the expectation value of momentum squared is gonna be um, integral over all space of the wave function, and because momentum has the position derivative in it, I have to be especially careful, not in ordering the terms. I have to make sure that I have my operator, momentum squared, which would be this thing squared. So minus I squared is minus 1, h bar squared is, well, h bar squared, and then position derivative, the second order position derivative, applying to this wave function, square root of, sorry, fourth root of m omega over pi h bar e to the minus m omega over 2h bar x squared, integral over dx. Oh, um, yeah, this is gonna yeah, I'm looking at this second order derivative, and um, I'm gonna do this partially using computer algebra system. So let me first simplify this a little bit. I can pull out the constant coefficient. The fourth root times the fourth root becomes the square root of m omega over pi h bar. Let's see here. This exponential will remain the same. Oh, I should have pulled out minus h bar squared. So let me write this out here. Equal to minus h bar squared. All right, so this portion, the derivative, second order derivative of this, I'm gonna do that on my computer algebra system because I don't want to do it by hand. I do know I can do it. So it's exponential of minus alpha x squared second order. Okay, that's what I have. All right. Okay, so that's my expression. Let me just preserve this e to the minus alpha x squared. That's gonna combine with this first one. And for in between, this is what I have. Integral of negative infinity to infinity, 4 alpha squared. So here I have to be careful here. This is my alpha squared. Oh wait, I guess that's what I was using before. So yeah, so let me write this all out. 4 times alpha squared, m squared omega squared over 4 h bar squared times x squared. That's the first term, minus 2 alpha, 2 times m omega over 2h bar. Let me just cancel some of these terms. And for the exponential term, this is what they'll look like. They multiply to this commonly, so there's the exponential term from here, and there's the other exponential term. So it's gonna be e to the minus m omega over h bar x squared dx. Okay, this integral is actually something that you should have memorized because this is what we kind of started out with in part A. The integral of this e to the minus alpha x squared is square root of pi over alpha. So that's what it's gonna be. So integral of just this portion here with the second term is gonna give me square root of pi over alpha, or pi times h bar over m omega. Now this term here with e to the minus m omega, so the x squared portion is gonna end up in um, square root of I think it was pi over 4 alpha to the third power. Yeah. So it's gonna be pi alpha to the third power h bar to the third over 4 m to the third omega to the third. So yeah, let me just write this out so that I can simplify them, and we'll see where we are at. Minus h bar squared square root of m omega over pi h bar. So these are all constant coefficients that were included in this result. So I have m squared omega squared over h bar squared times, now the result from the integral, square root of pi h bar to the third over 4m third omega to the third minus these coefficients that were not part of the integral, m omega over h bar times the square root of pi h bar over m omega from the integral. All right, let's see what cancels. Think, yeah, this leading term, it does a lot of good cancellation. So I can see this entirety cancels this entirety. And let me just make sure I do this cancellation right. So m cancels out one factor of m, omega cancels out one factor of omega, h bar cancels one factor of h bar, pi cancels out pi. Good. So I have square root of h bar over 2m omega squared. So, so this is gonna be, so one factor of h bar that cancels this, one factor of m that cancels this, one factor of omega that cancels that, and I have two remaining still. Okay, so I have m omega over 2 h bar minus m omega over h bar. Oh, so this actually whole thing simplifies into this. The algebraic clusters are the same, so this whole thing ends up being minus 1/2 m omega over h bar. So h bars cancel, or well, some of it can, let me just go through this. Minus signs, they cancel each other, and putting it all together, I have 1/2 m omega h bar squared over h bar, so just h bar. So that is my expectation value of momentum squared. And after all the simplification is done, it looks quite simple. And I do recommend for something like this that you do all the simplifications fully, because there's a greater chance of making a mistake as you type in the expressions. So yeah, so that's the result for part C. And what's left here as a comment is that when you have this expression and you have this expression, you see that when you multiply them together, m omega cancels out, and you are left with 1/4 h bar squared. So you get this result that the expectation value of standard deviation squared of x and standard deviation value squared of momentum is h bar squared over 4. So if you imagine taking square root of everything, you end up with h bar over 2, which is the minimum allowed uncertainty under the Heisenberg uncertainty principle. It's quite elegant result. And not all states have this minimum uncertainty condition. You will find that ground state of particle in a box, for example, don't have this property. It's only a few known wave function solutions that do have this property. All right, keep going. Question 7. For the simple harmonic oscillator ground state, yeah. Oh, using this fact, you can estimate the ground state energy. Follow the steps below for this calculation. Um, all right. Mm, Um, sorry, because this question appears related to the previous question, I think I was wondering if I could reuse some of the calculation, but maybe I don't need to. I'll just follow through the instructions. So it says to write down the total energy of the ground state in terms of delta x squared and delta p squared. All right, let me do this first. So I'm going to write down the um, so let's say we have the ground state wave function psi naught of x. Then the total energy. Well, total energy is kinetic energy plus potential energy. So in terms of operators, this is gonna be momentum squared over 2m plus potential energy for simple harmonic oscillator is 1/2 m omega squared x squared, x as operator. So um, yeah, so I guess you can imagine doing this. If you are imagining taking the expectation value of the total energy, I mean, this is energy eigenstate, so you don't have to take the expectation value. But in order to connect to these expectation value expressions, you can imagine taking expectation value anyway. It doesn't hurt anything. So when you take the expectation value, and I'm gonna use the shorthand expression. So all this expectation value, um, it's a shorthand for this whole integral thing that I would eventually need to do. So minding that, what I can write down is so this 1 over 2m, it's just scalar multiplication. So all this integral that I will do in the end doesn't affect it. So I can write this first term as 1/2 expectation value of momentum squared. And also because this expectation value calculation is integral, and this additions, you can always separate out into two integrals so I can do expectation value of one and then the other. For the second term, it's going to be plus 1/2 m omega squared, all constant, times the expectation value of x squared. Oh, I guess that's what this question is getting at. So for each of these expectation value expressions, I'm going to follow the hint and write this as delta p squared, and this is delta x squared. I think that's what this instruction is trying to guide me as delta times p squared. And I'm going to follow the advice here, write it as this. And format hint, this is distinct from this. So distinct in terms of what it ought to mean and how the system actually interprets the algebraic expressions here, delta x squared. Because I think it's treating delta as just another variable, not anything else. Okay. I did that. Oh, I forgot m. It's 1/2 m here. Again, this is the hallmark of a lot of quantum mechanical calculation, which is that there are tedious details you have to keep straight. So keep track of your algebra and be ready to make some mistakes and correct it when the system tells you it's wrong. This is actually a good thing about MyOpenMath auto-graded systems, because you can spot those. You can see that you made a mistake and spot it and fix it. Okay, it says now we bring in quantum mechanics. Now, anyways, for minimum uncertainty state, right, that is correct. And previously we derived, and do I repeat it here? well, before in the previous question, we derived that for this ground state, it actually does obey this minimum uncertainty condition. So the calculation we are doing here, yeah, it, uh, don't expect it to hold for everything, but it does happen to hold for this particular state. So, okay, let's see here. Instruction here is rewrite the total energy in terms of delta x only, constant parameters and on omega the characters. Okay, so what I have is, so in P, what I have is, okay, delta x, delta, well, sorry, let me first copy down the result from A above, which is that my total energy can be expressed in terms of these uncertainties. 1/2 m delta p squared plus 1/2 m omega squared delta x squared. And what this is equation with too many unknowns. So we are trying to figure out the total energy. Oh wait, let me not use T because that actually has different meaning in different contexts. Total energy. It has two unknowns: delta p, the momentum uncertainty, and position uncertainty. And technically, the energy is also an unknown. So too many unknowns. We are trying to reduce the number of unknowns, and one way to do that is introduce additional relationships, which is this minimum uncertainty relationship. Uncertainty in position, and this definition wise is delta x squared square rooted again, just minding that, times delta p is equal to h bar over 2. So since I want to express the total energy in terms of delta x only, I think what I want to do is solve this for delta p. Then it's h bar over 2 times uncertainty in position. So plugging it in here, I get my total energy is equal to 1 over 2m times h bar squared over 2 squared 4. And this is delta x squared. I'm going to write it as delta, just 1, x squared plus 1/2 m omega squared delta x squared. Yeah. All right. Oh, yeah. So here I'm explicitly relating the uncertainty in momentum and uncertainty in the position. So I haven't actually applied the minimum uncertainty quite yet, because so far all I've done is this is the relationship between them. So this is looking complicated, but that's fine. I hope it's gonna simplify in the upcoming steps. So I'm just gonna replace the delta p squared with h bar. So h over 2 pi squared divided by 4 times delta x squared. All right. Oh, wait. Okay, so that should be it. Yep. And in part C is where we now try to assert that, well, what's the minimum we can get these, well, how do you put it? So you can look at it this way. You can look at it as, I have some expression with 3 free parameters. I've constrained one of them by insisting that Heisenberg uncertainty principle holds. Yeah, that left me with 2 variables in my equation. And what I'm going to do is I'm going to constrain this expression further by saying that I'm going to look for a total energy that's consistent with this expression here while minimizing it. So I'm trying to look for, the ground state, the minimum energy state possible. So that's what I'm doing. And the so the question says using calculus, and the calculus procedure for this is pretty simple. Um, what you do is you take the derivative of the total energy in terms of delta x, and you set that derivative equal to be zero, so that you have minimum possible uncertainty in terms of delta x. So let me do that. Wonder if you know what? Let me do this calculation a little bit simpler for myself, and I think I can insist this in terms of delta x squared. I think that's gonna. So let me just do a quick substitution of this delta x squared as my, I don't know, parameter capital D. So I'm taking the derivative with respect to capital D of 1 half m h bar squared over 4d plus 1 half m omega squared d. I think that calculation will still lead me to the same final result. So the first term, I get minus h bar squared over 2 times 4, 8, and then d, I got this minus from d to the minus 1, bringing the exponent down as coefficient, and then the new exponent is d to the minus 1 minus 1, so it's minus 2 here, plus 1 half m omega squared, and d just goes away. That's kind of why I wanted to do it this way. Set this equal to 0, and I'm gonna solve for d here. Oops, no minus 2 there. Putting in the denominator is my version of minus. So solving it for d, what I end up with is, I'm just going to do most of it in my head. So I imagine moving this over, and then move d over by multiplying both sides by d squared. And on the other side, I have 1 half m omega squared, and then move all this over, so m's cancel out. Wait, so not cancel out. I have m squared, omega squared, 8 over 2, so 4, divided by h bar squared. So my d becomes square root of all this, or 2m omega over h bar. So this is my delta x squared. So for my delta x min, I need to take another square root here. And when I do, this is so this is the uncertainty in the position, which will minimize the total energy. That's a square root of this. So square root of 2m omega over h bar. Okay. Guess I'll plug that in. Square root of 2m omega over h bar, or h over 2 pi. Again, I need to do it this way because the system won't recognize h bar. Did I miss something? Let's see here. Let's see. I think I'm okay up to here. D squared is 4m squared omega squared over h bar. squared. And let me just make sure I'm using only the allowed variables, m, omega, and h. Okay. Hmm. Let's see here. Just gonna imagine putting this in here. I see. I think this is the reciprocal of what I should have written. Yeah, sorry. This is what happens when you try to do the algebra in your head. So, the thing that I was trying to do in my head was 1/2 m omega squared h bar squared over 8m d squared. Solve it for d squared. So it should be d squared is equal to, goes over here, the rest moves over here, h bar squared over 2 over 8 for m squared omega squared. So it's the exact reciprocal of this. No, no, me doesn't cut and paste maybe. Okay, 1 divided by. All right. Yeah. Tedious algebra. It bane of shortcut takers. All right. Okay. So for part D, um, I know what the answer is, so I'm just gonna write in the answer. Here, the answer will end up being h bar, so, or h over 2 pi times omega, and not ending there, it omega divided by 2 because it's the ground state. And when you plug in the value of delta x mean into these and you go through the algebra, this is what you will get. And the node at the end is normally an estimate like this is just that, an estimate. There's a great deal of connection between estimate of this kind and what we call dimensional analysis that you will see me do later in the class. And anyways, so this kind of estimate usually gives an answer that's within an order of magnitude. Here, because of the property of the simple harmonic oscillator ground state, it ends up being the exact answer. So, all right, that's question 7. Wow, that's already been close to 2 hours. Let's just keep going. Or do I want to? Yeah, actually, this far is how far I wanted to get to um, last virtual class session, but I didn't quite. So let me just call this part 1 and end it here. And I will do the remainder in part 2 in the virtual class session today. And yeah, so let me just stop the recording here and upload this so far. Thank you for watching. Until next time, bye.